Reactive elements tend to gain or lose or share electrons to fill their outermost shell. A cation is a positive ion. A positive ion is formed when an element loses an electron. Remember, an electron has a negative charge. So if an atom, let's say nitrogen here, has 7 protons and 7 electrons, and it lost 1 electron, then it would have 7 positive charges, 6 negative charges, and have a positive overall charge. It doesn't work this way for nitrogen, but nitrogen's up there on the slide. So losing an electron means that there are fewer electrons. It produces a positive charged ion called a cation. And there can be cations with a charge of 1, positive 1. That means it's lost 1 electron. If it's lost 2 electrons, it has a positive charge of +2. If it loses 3 electrons, a positive charge of +3, and so on. So here's sodium. Sodium has, well, let's count the electrons. 2 in the innermost shell, 8 in the second shell, and 1 in the outermost shell. So it must have an atomic number of 11 protons and 11 electrons. That 1 electron in the outermost shell, well, would it be more energy efficient to lose that 1 electron, or would it be easier to gain 7 to have a stable outer shell of 8? It's much easier to lose 1 electron. So sodium always loses that 1 outermost electron. Therefore, it has a positive charge of +1. Anions are negative ions. You can see that word anion itself, a negative ion, anion. In a reaction to achieve stability, gaining an electron means it becomes a negative ion, an anion. If you gain 1 electron, you'll have a charge of -1. Gain 2 electrons, charge of -2. Chlorine has, well, again, let's count the number of electrons. 2 in the first shell, 8 in the second shell, and, oh, over there on the far left, you can see it's missing its electron right here, so it only has 7. 2, 8, and 7 is 17. It's much more energy efficient to gain this 1 electron, and it will have a positive charge, a negative charge of -1 with that 1 extra electron. This is the chloride ion. What type of ion will oxygen become? Well, you have to look at the periodic table, determine how many electrons are in the outermost shell, and determine whether it will lose electrons or gain electrons and how many. So you might want to pause the video while you do that and see if you can get the right answer. Chemical bonds. A bond is an electron thing. Bonding is caused by electrons. So atoms will interact with other atoms to have a stable outer shell of 8. And this results in a chemical bond. Making or breaking a bond is called a chemical reaction. Well, a common type of chemical bond is the ionic bond. We have just seen how ions form. Sodium loses an electron to become a +1 ion. Chlorine gains an electron to become a -1 ion. When there are equal and opposite charges, they're attracted to each other. Sodium is attracted to chlorine, and they form the ionic bond, sodium chloride. So when you think of an ionic bond, always think of salt, sodium chloride, and how there has been a transfer of 1 electron from the sodium. That's the one that the chlorine gained. They're right next to each other in space. So the sodium loses an electron to chlorine. They both become ions, and they're attracted to each other. And this shows that entire process. Now, when you have an ionic compound, like salt, salt is a general term. Most of us think of table salt, but when you have different atoms together, they can be salts. For example, potassium and chlorine form a salt. Magnesium and chlorine form a salt. Salts are not, these ionic compounds are not molecules. Because of the charges, they're attracted to atoms of the opposite charge. So it forms what's called a crystal lattice. So salts are crystals. And here you have every single negative ion, the chloride ion, is going to be surrounded by all these positive sodium ions. Covalent bonds are completely different. Those outer shell electrons are called valence electrons. Covalence means together valence. So what happens is two atoms come close together, and remember their electrons are moving very rapidly around the nucleus. And instead of transferring one electron from one atom to another, the electrons start moving around both nuclei, and they share those outermost electrons. So we use the word sharing of electrons for covalent bonds instead of transfer. In ionic bonds, electrons were transferred. Here in covalent bonds, they're shared. And covalent bonds form molecules. Here are examples of nonpolar molecules. I didn't mention nonpolar, but when those electrons are shared equally between the two atoms, that is, one atom has one electron, the other atom has one electron, they each have one proton each. The protons are attracted to the electrons, and there's equal sharing between those electrons. There's no more pull of one electron to one atom or another. Those are nonpolar molecules. Sometimes one of the atoms has more protons than the other atom, right? Different atoms have different numbers of protons, and so it would have more pull toward that electron, so the electron would spend a little bit more time around the bigger atom that's got more protons. For example, water. So water is our key molecule to tell us, to represent polar covalent bonds. Water's the Mickey Mouse molecule. That oxygen has got a lot of protons in the center of it, and it attracts those electrons from each hydrogen. So while these electrons are shared between the molecules, the two atoms, the three atoms, the oxygen atom, in red here, has a slight negative charge, and that delta negative represents a slight negative charge. There's a negative pole here around the oxygen atom. Each hydrogen has a slight positive charge. The electrons spend more time around the oxygen than they do the hydrogen. The electrons are not equally shared. This is a polar covalent molecule. Negative pole, positive pole, and this gives water its unique properties that allow life to exist on Earth. So bonds form between polar molecules, for example, between water molecules. And what happens is, I'll show you the picture. It's easier with the picture. The molecule is set up so that a negative charge here on this oxygen is attracted to the positive of this hydrogen all throughout every molecule. They're all aligned so that positive and negatives are near each other. Small positive charge on hydrogen atom of one molecule is attracted to the small negative charge of oxygen on another molecule, and this gives it a special name, the hydrogen bond. We'll see hydrogen bonds between other molecules as well. For example, proteins are held in their shape by hydrogen bonds. But a hydrogen bond is a weak bond, very, very weak, but there are usually so many of them. And next we want to talk a little bit about chemical reactions. A chemical reaction is just making or breaking a bond. There's nothing special about it. In this equation up here, we see that hydrogen and oxygen make water. So in our body, we are making or breaking bonds constantly. So there's some definitions we need to know here. If you are on the left side of the arrow, you are a reactant. So here hydrogen and oxygen are reactants. The arrow points to the product, which is water. And if you added up all the chemical reactions in the body, all the making or breaking reactions, this is called metabolism. So some making reactions or building reactions would be making proteins. A breaking down reaction would be digestion. So in order to form water, these bonds have to break. The hydrogen bonds have to break, the bonds between the two hydrogen atoms. It's a nonpolar covalent bond breaks. These bonds break, all these bonds have to break, and new bonds have to form. We won't worry about balancing equations. This equation, if you've had chemistry, you'll know that this equation up here is not balanced. That's okay, we don't worry about it. What particles of two atoms interact to connect the atoms to each other? What two subatomic particles of two different atoms interact? And you should know that electrons of one atom interact with the electrons of another atom to connect them. Well, we use chemical reactions to provide energy, to maintain homeostasis, essential activity. Well, here we go. Substances absorbed are nutrients. So everything you eat is going to go into your body to form every single part of your body. So we will break down those nutrients. Our mitochondria will produce ATP in order to grow, to divide, maintenance and repair, special functions. A little bit about work and energy. Work is the movement of an object or a change in the physical structure of matter. So it can be moving your muscles, contracting your muscles to move, or it could be microscopic, such as the formation of molecules. Energy is the capacity to do work, and there are two kinds of energy, the energy of motion and the potential energy. In our body, we talk a lot about potential energy because the nutrients we eat have potential energy. It is stored energy. Cellular work includes producing complex molecules, moving materials into or out of the cell. And keep in mind that anytime we transfer energy, that is, if we take the energy of our nutrients to the energy of motion, it's not 100% efficient. A lot of energy is lost. In our bodies, that energy is lost as heat. And so as we exercise more, our body temperature will increase as we move those muscles. When the muscles are contracted, the potential energy of the nutrients in the muscles is converted to the kinetic energy of movement. A little bit about chemical notation. Atoms, our periodic table consists of elements, and the elements all consist of atoms of exactly the same type. If you have a number preceding a symbol, H is the symbol for hydrogen, it tells you have two hydrogen atoms. A chemical formula tells us a little bit more information about how many atoms and what type of elements are in a reaction.